Hi, everybody. So now let's try to prove a few basic theorems about isomorphisms so that we'll have some properties that we can rely on as we use them to try to study relationships between groups. So these properties are sort of a combination of the fact that F is a bijection and that it has the property that it preserves multiplication, transfers the multiplication in G to the multiplication in H. The first property is just a consequence of the fact that F is a bijective map, and that is that G and H have the same number of elements, or if you like, the same cardinality. If you talked about infinite sets in Math 2710, then you know that two sets have the same cardinality if they have a bijection between them. So this is almost just the definition. In the case of G and H being finite, then if you have a one-to-one correspondence between two sets and they're both finite, then they have the same number of elements. So this is just a consequence of F being bijective. The next thing to notice is that so F is originally a map from G to H, so there's an inverse map that goes from H back to G. And we know that the map in the direction from G to H has this property that F of AB is F of A times F of B. It turns out that the inverse map also has that property. In other words, the inverse map is also an isomorphism, but it goes in the other direction from H to G. So we need to check that F inverse of H1, H2 is F inverse of H1, F inverse of H2 for all H1 and H2 in H. Because remember, F inverse is a map from H to G. So given H1 and H2 in H, let's just write H1 we know is F of G1, H2 is F of G2, and H1, H2 is F of G1 times F of G2, but that's F of G1, G2 because F is an isomorphism. And now let's read these using the properties of the inverse function. This one tells us that G1 is F inverse of H1. The next one tells us that G2 is F inverse of H2. And the third one tells us that G1, G2 is F inverse of H1, H2. But on the other hand, G1, G2 is certainly also equal to F inverse of H1 times F inverse of H2. That's these two equations right here. So, so this checks out. It just tells us that the inverse is also an isomorphism. And now that means that properties of G carry over to properties of H. So the first is if one of G or H is abelian, then so is the other. So let's suppose that we have an F from G to H is an isomorphism. And suppose that G is abelian. And suppose we have two elements, H1 and H2 in H, which we can write as F of G1 and F of G2. Then on the one hand, we have H1, H2 is F of G1, F of G2, which is F of G1, G2. But G is abelian, so that's the same as F of G2, G1. And that's, by the isomorphism property, the same as F of G2 times F of G1. But F of G2 is H2, and F of G1 is H1. So by taking our elements of H kind of finding representatives for them in G, we can switch them in G and then go back, and therefore we must have been able to switch them in H. And you can go the other direction, since F inverse from H to G is an isomorphism. You can use the same argument to show that if H is abelian, so is G. So isomorphic groups, if one is abelian, so is the other. Well, even more. If you have two cyclic groups, if you have two groups, one of them is cyclic and there's an isomorphism, then so is the other. So F is a map from G to H. Let's suppose it was an isomorphism. And we suppose that G is cyclic. Well, what this means is that there's a G is generated by some element G. And every element of G is of some power of little g. So let's let H be F of G. And I claim that H is generated by H. And why is this true? Well, take any element. Let's let, I don't know, H2 be an element of H. Then we know that H2 is some F of G2 because we have a bijective map, so it's an onto map, so every element of H is in the image of F. But we know that G2 is some power, it's G to some power I, because G is cyclic. So H2 is F of G to the I, which is F of G, F of G, F of G, I times. In other words, it's F of G to the I. But F of G is H, so this is H to the I. So H2 is H to the I, and what we've shown is that any element of H is any element of big H is a power of little h. And so we've shown H2 is H to the I for some I. So H is cyclic. And even more, if this is an isomorphism, then the image of a generator has to be a generator. And we did also see this in the case of Z6 and U of 7. You remember that we had the map F from Z6 to U of 7. The generator of Z6 was 1. And 1 went to 3 to the 1, which is 3, which is a generator of U of 7. So the fact that these are both cyclic groups of order 6, because there's an isomorphism, we showed that since Z6 is cyclic, so is U of 7. Of course, we all already knew that U of 7 was cyclic. That's how we constructed the isomorphism. But that's still an example of what's going on here. If you have a subgroup of a group, if K contained in G is a subgroup, and you take F of K, F is an isomorphism from G to H. Then F of K, which is the collection of H in H, so that H equals F of K for some K in K, is also a subgroup. So the subgroups get carried from one to the other. And to show this, well, how do we check that F of K is a subgroup? We need to show that it's non-empty. And that's okay because F of K contains F of E sub G, which is E sub H, because E sub G is in K. We know that K contains the identity element of G, So f of k contains the identity element of h, because we know that f of E sub g is f of E sub h. So f of k is non-empty. And suppose that a and b are in f of k. So a, therefore, is equal to f of k1, and b is equal to f of k2. Then a times b is f of k1, f of k2, which is f of k1, k2. And that shows you that it's, and therefore this since k1, k2 is in k, so then f of k1, k2 is in f of k, and that shows that it's closed, tells you that the product of two elements in f of k is again in f of k. And finally, we need to check that if a is in f of k, so in other words, if a is equal to f of some k, well then, what about a inverse? Well, I claim that f of k inverse is equal to a inverse. And why is that true? Well, let's check. If we multiply f of k inverse times a, well, that's the same as f of k inverse times f of k, which is the same as f of k inverse times k, which is f of the identity, which we know is the identity in, I guess I should put E sub g and E sub h. So f of k inverse acts like the identity of a, and therefore a inverse is in f of k. So the image of a subgroup is a subgroup. And finally, if one of G or H has a subgroup of order n, then so does the other. That follows from the preceding result. Because if K contained in G has n elements and is a subgroup, then f of K contained in H is a subgroup, and it also has n elements. So if G and H are isomorphic, and one of them has a subgroup of order 3, then the other one also has to have a subgroup of order 3. And if you put all this together, what you find is that, in fact, isomorphism is an equivalence relation on the set of all groups. In other words, we can divide up groups into equivalence classes by isomorphism. And so remember, to check that it's an equivalence relation, we need to check the three properties, that it's reflexive, symmetric, and transitive. So to be reflexive is to say that G is isomorphic to itself. In other words, we have to find a map F from G to G that's an isomorphism. And we can find that because we can just take the identity map. The identity map, which just takes G to G, is clearly an isomorphism because it's bijective, and G times G is G times G. G1 times G2 is G1 times G2. So it's a reflexive relation. We proved already that it's symmetric because we proved that if F from G to H is an isomorphism, then F inverse from H to G is 2. We already proved this. So we've shown that it's symmetric. So I guess we really just need to check the transitivity. And for that, we need to know that if we take F from G to H is an isomorphism, and G from H to K is an isomorphism, then we need an isomorphism from G to K, and the obvious one to take is G composed with F, which takes you from G to K. So if these are isomorphisms, then the composition is 2. And for that, we know that it's bijective. That's a 2710 fact. G composed with F, if both of these maps F and G are bijective, then G composed with F is bijective. And if we want to check G composed with F of G1 times G2, that's G of F of G1 G2, which is G of F of G1 F of G2. And this is a product of elements in H, and G is an isomorphism, so this is G of F of G1, G of F of G2, and that's G composed with F of G1, G composed with F of G2. So the composition of isomorphisms is an isomorphism, and therefore the relation is transitive.